I am going to present about the pulsar search in GHRSS survey. These are the three central sky GMRT antenna looking at the zeniths. So let's start with the contents. So first I will explain about the introductory part, then I will explain about the pulsar search and pulsar search with GMRT. Then I will tell about the GHRSS survey and implementation of machine learning in GHRSS survey. Then finally I will summarize the overall talk. Let's start with the introduction. So pulsar are highly rotating magnetized neutron star. Those emit a beam of electromagnetic radiation. When this pulsar means when this beam of electromagnetic radiation crosses our line of sight, this looks like a pulsation of radiation. Hence they are named pulsar. So a special class of pulsar called millisecond pulsar having a periodicity value less than 30 millisecond. These are known as timekeepers because of their high periodic stability in the order of 10 to the minus 17 to 10 to the minus 21 second per second, and they are the strongest magnets we know, having a magnetic value of 10 to the minus 8 to 10 to the minus Gauss, which is billions times the magnetic field in Earth. So what are the difference between the normal pulsar and millisecond pulsar? So as I told, the millisecond pulsar has a periodicity of less than 30 millisecond and normal pulsar greater than 30 millisecond. The millisecond pulsar mostly found in most denser space like a globular cluster, and normal pulsar often found in globular galactic plane. And their magnetic field of MSPs are quite low compared to normal pulsar, that is 10 to the 8 to 10 to the 10 Gauss for millisecond pulsar, and for normal pulsar it 10 to the 12 to 10 to the 13 Gauss. Here in the right side of the plot you can see that this is a P versus P dot diagram. The data is taken from ATNF catalog. You can see that there is a bimodal distribution of pulsar. The left side lower left side distribution showing the MSP having more means lower value of periodic derivative, and the right upper one showing the normal pulsar having the higher periodic derivative value. So MSPs are often used in to detect gravitational wave in PTA due to their less period derivative value and less red noise. So PTA is a pulsar timing array, uses array of MSP to detect the gravitational pattern in their TOS. So why to search for new pulsars? So simulated galactic population saw that there are 40 to 90,000 of MSPs are there, but as we know now, out of total non-pulsar population, only 17% are MSP. So that's why this doesn't represent the true distribution of the MSP. That's why we are hunting for more pulsar. So, sir, there is some application of pulsars like knowing the structure of neutron star and its evolution, probing the ISM, and also to study the relativistic dynamics in binary pulsars, and to trace to probe the ISM and trace the Milky Way galaxy. So, a new pulsar will expand our knowledge into detect the gravitational wave, to map the galaxy, and to explore the space. Then what and how we are doing the pulsar search? So pulsar search, as I told, pulsar are rotating neutron star, they emit electromagnetic radiation. So we have to identify this rotating neutron star signal through our telescope. So there are two type of search, that is blind search and target search. In blind search, you don't have any idea about the target. You just focus your telescope toward the sky and observe the data, and you just search for pulsar. In target search, you have some idea about this about your target, and they focus your telescope, and after that get the data. Some of the blind search is one of the GHRSS search, which I will explain in upcoming slides, and some targeted search are GCGPS and scope and supernova element. So what are the process of pulsar search? First, the signal are astrophysical in nature. That's why when it is reaching the telescope, different frequency reach at different time. That's why we account for the dispersion to correct for the time delay between different frequency. After that, we will do the FFT based search or FFF based search to detect for any normal millisecond or normal pulsar. There are some challenges in the search like RFI, which is a major problem in high computational demand, and some of the advanced search includes the acceleration search, jerk search, single pulse search, and implementation of machine learning algorithm. Then GMRT, as all of you know that geometry consists of 30 steerable parabolic discs, each having 45-meter diameter, having spanning a frequency range from 0.1 to 1.46 GHz frequency, having wider bandwidth 200 and 400 MHz for different bands. So geometry excelled due to its low frequency coverage, broader bandwidths, and precise localization capability. And you can say that for the uncertainty in the TIS in the order of sub-microsecond for 10 minutes of band 3 observation. And these are the band information and typical uses of different bands. And these are the antenna, central square antenna of GMRT. So GMRT means for pulsars, as like pulsars are having steeper spectral index. So means higher flux density as lower frequency, so which favors the low frequency observation, where this GMRT bands are there. So GMRT has a large collecting area, as I told, the 30 parallel discs is having 45-meter in diameter, and multi-beam forming capacity, PA beam, IA beam, and simultaneously different beams with different bands. And high timing sampling time resolution is around 81.92 microsecond to detect the MSP. And we also do the follow-up observation with GMRT, like log type timing behavior, binary probing the different phase of binary orbit, and glitches and rotational irregularities. Example of some surveys, ongoing surveys are GHRSS and GCGPS and GMRT targeted discovery with formula directed search. So let's about it. GHRSS is the GMRT High Resolution Southern Sky Survey, which is a off-galactic plane survey designed to hunt for pulsar and radio transients, which is in the range of declination range of -20 to -54. It is operating in blind mode, means IA beam, so to get the more sky coverage in a single observation, and it is operating at band 3 with and it's occurred two phases. At phase 1, it's uses the legacy geometry data, which is having a central frequency of 322 megahertz, having a bandwidth of limited bandwidth of 33 megahertz, and with UGMRT, that is at phase 2, which is the ongoing ongoing phase. We are using 300 to 500 megahertz frequency, having a bandwidth of 200 megahertz. So different detection levels are mentioned here. For a 2 millisecond pulsars with 10% duty cycle, for a 10-minute of observation using 17 GMRT antenna. Till now, we resulted in 31 discoveries. So this is the sky coverage of the GHRSS survey, and in the right side, in these points showing the each individual I beam points for cover the entire area, and the bold point represent the whole halls. Those are remain unscanned during the previous observation. So we are taking the new observation for covering these halls, and this pointed like blue and green color showing the discovery of the GHRSS survey. Typically, we are giving 10 minutes for each scan using IA beam, and ongoing observations are going on to cover the remaining halls. This is the entire flow chart we are following for the GHRSS survey to hunt for pulsar. So first you will get with, after the observation, you will end up with the raw data, you will do the RFI mitigation, then account for the dispersion for multiple DM values, then we will be search for pulsar using FAA based search or FFT based search. And after that, we will find for any candidates and save for further confirmation. So in the FFT-based search, we have enhanced the pipeline by taking the DM value up to 250 per sec per centimeter cube, why 250? So here in the left side of the plot, you can see that the fractional number of pulsars versus DM. So in the blue bar showing the fractional number of MSP, and the yellow bar showing the fractional number of normal pulsar. So you can see the up to 250, if you are continuing with up to 250 DM, it is almost covering 93% of the MSP and 71% of the normal pulsar. And this bigger bar is at around DM 250 is coming from the contribution of globular cluster. In the right side of the plot, you can see that if you are taking the DM up to 250, then it is almost covering 86% of the MSP having different acceleration. Having highly acceleration MSP. So in total, if you are taking DM up to 250, then we are it includes the total 88% of the total non-population of pulsar. Then again, after we modify the DM script for means to include different various DM step. For DM from 1 to 30, it is mean DM state is 0.01, and so on from DM 110 to 250, the DM step is 0.1. This is due to the at higher DM, the intra-channel dispersion between two channel will be increased. That's why we are not searching very deeply in DM for high DM values. And in total, we are ending up with around 6900 DM step, starting from 1 to going up to 250 DM values. And after that, we have implemented the FFA pipeline for means for normal pulsar search. In the traditional, in the FFT based search, the means in FFT based search, it means normal pulsars used to lose sensitivity due to normal pulsars are more wider in time. So it will its means its power will spread across different different harmonics. So it will be very difficult to search in FFT based search. That's why FFA approach. FFA approach started, where we will do the time damping fault in different period of trial, and that you that we are doing with use of riptide. And the overall process is like that: first we will do the RFI mitigation, then the dispersion, then baseline correction, then we will do the FFA search, and finally we will account for the candidate clustering and visualization. In the right side of the plot, I have just simply plotted shown a time series of pulsar having time period of 1.2 second, and after doing a trial period search over various pulse dim, this is a phasor diagram showing the y-axis showing the time period and x-axis showing the pulse phase. It is from pulse 0 to 1. If it is means plotted in from 0 to 10, then it would be a it would be easily seen that this is a pulsar. And after that, it will detect the peak of this peak from this plot, and it will finally fold the data with that trial periodicity. See, the beauty of the FFA search is that it uniforms sensitivity across all the period and duty cycle. And from this paper, the 6 pulsar has been detected, out of which two are missed by the FFT based search. And from this example of discovery, you can see that it can detect the extreme knolling pulsar and very low duty cycle pulsars. Then the another thing is that after 10 minutes, for a 10-minute observed data, if you are searching for FFA and FFT by search, you will end up with around 50,000 plus candidates to look one by one. So inspecting all the candidates with eye is too much challenging, and there is a chance that you will skip any positive candidates. That's why we need machine learning like GHBFDT, which will automate all the process of candidate selection. What exactly it will do? It will take the candidates, it will apply the machine learning algorithm, and it will give us a list of positive candidates. Then we will inspect through our eyes and means account for its discovery. The machine learning uses machine learning scoring scheme based on some algorithms, and it also uses the pattern recognize with ML. And after that, we have to train the machine learning within use the telescope noise and RFI and label data. And after that, our main target is to find zero false positive and zero false negative and very low false positive. So in GHRSS survey, we have implemented the GHBFDT machine learning, which will take the two diagnostic plot from the folded profile. One is integrated profile versus phase, and another is DM versus SNR. And after that, it will account for this this much property of these two profile. And after that, it will generate a score based on its properties, and it will give a list of positive candidate and negative candidate. And this model is developed by this model is trained for GMRT noise and RFI by master's thesis student Arpit Kumar. So earlier we are looking all the folded candidate by eye. So we again refilter all the candidates using the GHBFDT machine learning, and after that we end up with some good candidates. And after that, we re-observe those candidates, and these are the folded profiles. Some of the candidates, and this is the list of publication where this listed all the 31 discoveries, and this is the list of publication. And now our target is to discover Mar pulsar and do the follow-up timing study, polarization study, and other application. To summarize the talk, means GHRSS survey result in 31 discovery, and ongoing observations are going on, and the new pipeline is FFA and FFT based pipeline, included the machine learning is installed in various machine, and now we are analyzing the already archival data and new observed data. In the future, our key is to continue the analyzing the remaining data and to re-observe the some of the good candidates to confirm their nature, and for any positive candidate we will do the follow-up observation, timing study, and publication.
Questions?
Yeah, hi. Thanks for the talk. I was more curious about the machine learning approach.
Yeah.
So, I recollect this paper also talked about, I think, implementing the scheme as an online tool which can, like classify candidates very quickly. I was curious about the run times of running this classifier on data. How quickly do you?
The thing is that if you are having 50,000 candidates,
Yeah.
then typically it used to take around 6 hours or 7 hours, which is fine actually.
Okay. Okay. Yeah, thanks.
Any questions further? Anything on online? Yeah,
I just had a small question. For the FFT pipeline, you have taken a DM limit of 250, but
Yes.
for the FFA pipeline, it's 500.
Yes.
Why? Why are the two different?
Because I saw in the place in this plot that most measure of the fraction of the MSPs are reside in these 250 limits. So that's why, and the thing is that FFT search is computationally more expensive compared to FFA search. That's why for a single 10-minute observed data, FFT search will take around more than 1 day, and FFA search will complete within hours. That's why I just limit the DM range. This is the first version of DM search. After processing all the data, means all the existing data, we will again search with higher DM range.
I may have one quick thing. So with all the development, everything is happening. So what do you think is like most challenging to increase the discovery rate?
The one thing is that we have data, so we are very limited computing resources like in Bhima. So we have the constant to means use 5,000 hours per core. So that's limit our thing because we have archival data and those needs to process.
Yeah. No, the computing resources, I think everybody is
Yes.
for computing resources. But in terms of algorithm, do you see any particular place where you have to put more effort to improve or something? Just in general, yeah.
Okay.
I think that is true for all pulses.
Yes.
So, yeah.
So that I will say that means this FFT and FFA search, I think, won't detect any exotic system like high accelerating means binary pulsars, because while searching we are time sampling and there we are losing the sensitivity for it. So we can means redesign the search algorithm to hunt for that also, means extreme systems, exotic systems.
Hi, I was also curious if you're trying to look at these, trying to do some searches for these ultra long period pulsars with this data.
Period.
Yeah, like which has started to become like more prominent. Like we're finding these pulsars spinning very slow, 76 seconds with a few minutes. I was just curious if there's any effort being done with the GMRT in that.
Okay, now we are searching up to means 10 second periodicity. So we can search up to means more longer periodicity. So for that we have to means restructure our search algorithm. That we have to do.
Okay, thank you.
So just very quick. So which machine learning algorithm you use? Maybe I missed that. Which you mentioned machine learning, but
yes.
which algorithms?
Which
machine learning algorithm?
This is Gaussian Hellinger very fast decision tree. So it is like you means it is a decision tree where you have put it
Basically,
entropy.
decision tree.
Yeah.
Questions? Yeah.
Hello.
Yeah.
Yeah. So when you search for this pulsars, so, you used two way of searching, right? The FFA and FFT.
Yes.
So have you seen anything is performing good at slow pulsar or good at like fast pulsar? Anything have you seen? Like both are finding the same kind of
No,
pulsar?
sir. The FFT means best search is for means mostly for millisecond pulsar, and FFA based search is for means 0.1 second to 10 second means slow pulse means normal pulsar only. So this is due to at lower frequency. If you are means searching long period pulsar which FFT based search, then normally FFA means long period has means pulsars have means wider means wider in shape. So if you are doing a FFT, then their means power will distribute along across more harmonics compared to the MSP. And there is another issue of red noise also. So that's why you won't get detect the normal pulsar. Means it is very hard to detect normal pulsar on FFA based search. And FFA based search we cannot use for means normal pulsar because that will be computationally more expensive.
Okay. Oh, thanks.
Okay. So we'll move on. Thanks, Sapan.